Welcome to Finite Element Methods. Today we'll be discussing the 2D finite element formulation for unsteady or steady heat transfer problems. We'll be looking at the 2D quadrilateral isoparametric elements first, and let me discuss how we can formulate those elements. So what are the finite element steps that we want to establish? First, we want to establish the strong form of the problem. So basically, what is a partial differential equation that describes the problem of interest? We want to then establish the weak form from the strong form. Starting from the strong form, we want to reduce the continuity requirements. And from there, we can then develop first the residual error function, make the residual error function orthogonal to the weight functions, and then integrate by parts so they can then reduce the continuity requirements. We'll then discretize the spatial domain, so that's called meshing. We're going to mesh the domain, and that'll create multiple subdomains across the whole domain. We'll determine the element formulation stiffness and force vector, and that's for a single element. And that approximation function has unknown coefficients as nodal quantities. So we are selecting the approximation function as a very smart way, and we do that by making those coefficients the ones that are unknown at the nodes. And that's accomplished using shape functions. We'll then make sure that we can then plug in that approximation function into the weak form and then use a weak form Galerkin to determine the expressions for the stiffness and force vectors. Once I have that information, I can assemble a global system matrix. I can apply the nodal boundary conditions, and then I can then apply the essential and natural boundary conditions. And from there, we can solve the global system of equations in a very, very nice way. So those were the basic steps. From there, what we want to do, we have the governing equation. So let's look at the example here. Given the governing equation that we have, here Q is a heat flux generation or the heat generation in terms of the body. T is the temperature. D is the stiffness matrix or the conductivity matrix. Rho is the density. C is the specific heat. T is temperature, but T dot is a time derivative of temperature. And that's the governing equation in V. The weak form becomes, is going to be this, and we derive that already. Now this V doesn't go there, I apologize. But the way you do that, you take this residual, multiply by the weight function V, integrate over the domain, so you can get an error over the domain in an average sense. And so from there, you can integrate by parts to get this expression, which we derived in the very previous lecture. Here you can see I have discretized the domain either with 2D linear triangles or quadrilaterals. So this is my domain, a square domain. And here you can see the different quadrilaterals and triangular elements at times. And the goal is to be able to formulate the element over a single element or approximate the solution over a single element, then assemble everything together. Now, when I look at the shape functions for these triangular elements, we need to calculate the shape functions for every single element. And these are not very simple calculations. In fact, then also you have to plug this into your the weak form, and that's going to involve more operations. It's going to involve the derivatives of the shape functions, and that's going to become very cumbersome. You can see here every element has different shapes, different coordinates, and here every shape function for every element will be different. And that's may not be as convenient as what we would like to do. For the quadrilateral element, very similar story. I'm not going to even write the shape functions because they vary from element to element and they look different from element to element. But again, a lot of computational expensive calculations to be able to do that shape function calculation for every single element. So this is a weak form. I can substitute the approximation function. So this is the t is equal m bold times t bold, where t bold is the function of time. T dot is m bold t dot. N is the matrix of shape functions, which we can find. And for v, we're going to plug in m bold transpose. When we do that, look at all these derivatives we need to calculate. First, we need to find m bold, but then we have to find the gradient of those, and that's going to be a lot of work. It's not straightforward. So we can see that that's a lot of work to calculate these gradients. These shape functions are different for every element. That's not very convenient. And then we can go ahead for triangular linear elements. What we have here is 3 shape functions, and you will just then calculate the stiffness matrix and this term that looks like a mass matrix, but it's not the mass matrix. And then you go ahead and just calculate everything. For quadrilateral elements, you have 4 shape functions instead, but the basic procedure is the same. And we discussed that in the very previous lecture. So what are we trying to do? We're trying to find a systematic way. The way we're doing this is just not very efficient. And that's where we turn our heads to isoparametric formulation. We need to calculate the integrals over triangular and quadrilateral domains. Here you can see that I have a B bold transpose, D bold, B bold. All this stuff needs to be calculated for every element. But notice how the shape functions for all the triangles and quadrilaterals could be different. And the derivatives of the shape functions also change from element to element. And that's going to take a lot of work. On top of that, we have to figure out how to integrate these quantities over the domain, and that domain is not the same for every element. And that's another issue that we have here. So what we want to do is we want to figure out a way of systematically solving this problem, and we're not there yet. So what is the goal? What we want to do, an approach, a solution to this problem that I just discussed, because you can see here that every element is going to have different shape functions. We don't want that. We want something simpler. You can also see that every quadrilateral element also will have their own shape functions, and the integrals that need to be calculated are over arbitrary domain, and every element will have their own domain. So what if I'm able to perform a mathematical miracle? What if I'm able to take an element that has a shape and transform it into this natural coordinate domain? And you can see here that this node number 4 became that node, this node became that node, this node became that node, and this node became that node. If I can transform the domain into a regular domain, and every element across the system is mapped into this domain, something very powerful does happen, right? So what is that one thing that happens when I do that? If I think carefully, every element will have the same shape functions. Every element can be integrated from -1 to 1 and -1 to 1. If I can actually perform this mathematical miracle of taking every element and transforming it into this element, which I will call the master element, that'll be very powerful because the shape functions for every element will be the same. The integrals will be defined over the same domain. So how can we perform that transformation? So the key here is to interpolate the temperatures and field. So not only we're going to interpolate the temperatures, but now we're going to interpolate the coordinates using the same very interpolation functions for this domain. So let's look at the shape functions, right? These shape functions will be much simpler to define for this square element that goes -1 to 1, -1 to 1. But what I'm doing now is these coordinates here, x and y, can be mapped in such a way that when I plug in a value of -1 and 1 or 1 and 1, I plug it in here, this multiplication returns the coordinates of that node. And these coordinates, x1, x2, x3, x4, are the coordinates of these nodes here, the x coordinates of these nodes. Not of these nodes, I'm sorry, of these nodes. So I'm going to keep those coordinates in this vector. And these shape functions, when I multiply this by this column vector, this will have the ability of taking me from this coordinate system, from this domain to this domain. And that's very powerful if we can accomplish that. We will do the same thing for the y coordinate. We'll take the y coordinates for the node 1, 2, 3, and 4 and put them in this column vector. And then this row of shape functions will help me do the mapping. It will take values I put in here and return for me the y coordinate system in this location. Again, the shape functions are defined in this coordinate system, the natural coordinate system. And when I plug in those shape functions, and if I select the value, say 0, 0, and I plug it in here, that'll return the corresponding y coordinate system somewhere here in the middle. Very powerful idea. So now I have approximated the temperature over this domain, notice, using this equation. And then this is a transformation that allows me to go from here to here and from here to here. But this equation clearly represents a situation where I can go from here to here. Because the shape functions are only in terms of this coordinate system. So now I have to come up with these shape functions. How do I come up with that? I have 4 nodes. 4 temperatures are unknown. So using the Pascal triangle, I determined that this is the coefficients that I want, A, B, C, and D. With C and eta, they're varying from -1 to 1 and -1 to 1. And A, B, C, and D are the unknown coefficients that I want, but they're not defined in terms of the nodal unknowns. And that's what I really want to do. And I recovered that for 4 noded quadrilateral elements, I have these 3, but I need one more. So that's the one I want to use. Is at least bias of all the terms in this row. We also need to satisfy this Kronecker delta property. We can derive the shape functions using the approaches I discussed earlier. One way is to just use the product of the shape functions we have for 1D. So 1D, we had this one and this one. Just go ahead and multiply them in the 2 different directions to get different combinations. So for N1, I get this, N2 this, N3 this, N4 this. So let's see if that works. You can see here that if I plug in C and eta of 1, I get 0 for N1. If I apply C of 0 and eta of 0, that's in the center, it will have a value of 1/4. If you add all these 4 shape functions, you will get a value of 1. Let's look at shape function number 1 to see where that was. It's at this little left corner. So that's -1 and -1 for C and eta. So if I put C and eta of -1, I get 2 and I get 2. 2 times 2, 4. 4 divided by 4, 1. But you can see these 0 at all other nodes. When I plug in these coordinates here, I get 0. Another way to derive the shape functions is to use this equation, make this equation equal to T1 at -1 here, and so forth. So just basically plug in here the values of these coordinates and then determine A, B, C, and D in terms of T2, T1, T2, T3, T4. When you solve it and you plug it into the temperature field, you will get that the temperature is going to be equal to the shape functions times this column vector. Notice how I'm approximating the temperature function over this domain. I'm not doing it over this domain. We're not approximating solution over this domain. We're doing it in this domain. And the goal is that somehow I can transfer the results into this domain. Because this is much easier to solve the governing equation over square domain than it is for a quadrilateral arbitrary domain. And so that's really what we're trying to get to, right? So let's look at what's the problem here, right? We need to calculate these derivatives, and that's required by this B bold. If you recall, I had to calculate these gradients, and gradient of N bold is what I'm calling B bold. But that gradient is relative to in the XY coordinate system. That's the issue we have. I had to find this gradient here, but the problem is that N1, N2, N3, and 4, those are in the defining a natural coordinate system. Obviously, N1 is not a function of X directly, explicitly, but somehow I have to calculate these derivatives. So then, therefore, we have to use a chain rule to figure out how to get there by doing a change in variable. So this is a derivative I want to take as required by this calculation here in the weak form. So what I'm going to do, I'm going to use the shape functions and the chain rule. So what about if I calculate the partial of A and I with respect to C? If I take any of these shape functions, N1, N2, N3, and 4, and did this chain rule calculation, partial of A and I with respect to X times partial of X with respect to C plus partial of A and I with respect to Y times partial of Y with respect to C. You can see here that Y and Y cancels, X and X cancels, so that's definitely this quantity. I can also take the same shape function and calculate it with respect to eta. You can see here partial of A and I with respect to X with respect to eta plus partial of A and I with respect to Y with respect to eta. I encourage you right now to pause the video and then derive this equation so you can see that it works out very nicely. Now, I here can be any of these values, 1, 2, 3, 4. So the procedure is the same. What I want you to notice is I can write this in matrix format. So this is that, and then notice how this column vector can be here, this column vector can be here, and these are the same for both of them. For this is the same as that, this is the same as that. So I can put them in the column vector. I invite you to check it out. So multiply this row by this column. So this times that is this term. This times that is this term. So that gets added. The second equation, this times that is this one right here, plus this times that is this right here. So I have my second equation. And note that what I really want is this derivative. That derivative is this column vector here. How do I find that? Well, the good news is I know in N1, N2, N3, N4 in terms of C and eta. So I can calculate these derivatives. I actually do know what the derivative of X with respect to C is, and I know all these numbers. These are actually all numbers. This is doable. All I have to do is invert this to calculate these derivatives, which are required by the weak form. Okay, does that make sense? That's the approach we want to use. Okay. So we're ready now. We can invert J, in which we call the Jacobian. No need to worry. This is the information that contains the geometry. This is the only thing that tells you how the quadrilateral got mapped into that square. This contains all the information. And these are all numbers, by the way. Every element will have these matrices filled with numbers, right? And that's the one that gives you the mapping. This is the information that has that. We've been able to decouple it somehow from having to approximate the temperature over the domain, because now the temperature is only approximated over the square domain. I don't have to worry about anything else except to calculate this Jacobian, which I'll show later. But now I have to invert this, which I'll bring to the other side. So then I get this column vector, which is this one right here, is equal to J inverse, which is this one. And this is this column vector. I'm going to call this J bold, so J bold inverse. And this is something I have to calculate for every single one of them. I equals 1, 2, 3, and 4. So I have to calculate this 4 times, right? But at least J bold can be easily calculated. I'll show you how. And this column vector, these derivatives are easy. And the shift functions are the same for every element. So let's look at what's going on here, right? I have to plug in. So I have to come up with a way of plugging B bold, which is all this. Well, each column vector, which is this, is equal to J inverse times that. But J inverse is common to everybody. So I can factor J inverse out, and B bold just becomes this vectors that the column vectors, these 4 column vectors in the aggregate, that's a matrix. But I know how to calculate these derivatives. I can do that. Why I know that? Because I know N1, N2, N3, and N4. I know these ones in terms of C and eta. So in essence, I know how to calculate those derivatives. And guess what? These derivatives are the same for every element. J bold varies from element to element, but everything else is the same. So this element unique, this is the same for every element. I'm going to call it B bold N to differentiate it from this B bold here. This has to be calculated for every element. And these are the shape functions for every element. These are the same for every element, the shape functions. So these derivatives are the same for every element. This is the only thing that's in an element unique, and these are just numbers. How do I calculate the Jacobian? Let's look at that. So Jacobian requires these calculations, these derivatives. Well, let's look here. X is this. We already discussed that. This is how you map it from the quadrilateral, from the square to the quadrilateral. That's N bold times X bold. I have to find this derivative. So partial of X respect to C. That's partial of N bold respect to C, X bold. And I have to find the partial of X with respect to eta. And that's partial of N bold respect to eta X bold. I also have to find this one here and those partials that you can see here. So all I have to do is plug this with that, plug this one with that. Yeah, just plug all this in here, right? Partial of X with respect to C is this. Partial of X with respect to eta is this. And these are all numbers. I know I know all the coordinates of the quadrilateral element because I meshed the domain. So I know these numbers. I know the shape functions. So these derivatives should be easy to calculate. Let's look at dA here. This dA here is really, this is my quadrilateral. So I have a vector here, dA, dB. The cross product of that gives me the area. You can show that dB hat is this and dA hat is this in this coordinate system. So when I take the cross product, I find this, and notice that this is the Jacobian, the determinant of the Jacobian. You can multiply yourself. This times that minus this times that is the determinant. Clearly, that's what that is. That's the Jacobian, the determinant. So I can take that dA and make a determinant of J, and then dA just becomes deep C d eta, which is beautiful now, because now the integral is over deep C d eta, which is a very simple domain, the square domain. So I've taken the integral and be able to just make it very simple integral now. So let's keep looking at what's going on here. I'm going to do the same thing with this dA and this dA. I'm ready to plug it in. So this is the equation I have in the quadrilateral domain. I want to turn that into square domain. So let's try. So dA, anywhere I see dA, just make it the determinant of J deep C d eta. And the integrals become from -1 to 1. Anything that has dA becomes this right here. And again, J bold is the Jacobian, which can be easily calculated because we know the coordinates X and Y for those nodes. And I know the shape functions N1, N2, N3, and 4. So I can calculate these derivatives very, very easily. So I have that. This term is this term. This term is this term. And this term, we'll talk about it later. This one right here is a little more tricky. We'll talk about it. These are the heat flux applied on the surface, while these are internal heat generation. So this term requires a little bit more work. So the element formulation, you have 4 equations for unknowns. And this B bold and bold. So look at this, right? Another thing I want to show you is that this B bold is J inverse times B bold N, right? So that's J inverse B bold N. So that's what I've done. Plugged everything in there. Everything else stays the same. So let's look at this carefully then. B bold N is all this stuff. I can find those derivatives very easily, right? Because we know the shape functions. I invite you to check it out, to do it yourself, so you can see that this is correct. And notice how this column here is essentially this column here. Isn't that B bold N? And this column here is basically the same thing you see here. That's B bold N also. So in fact, the Jacobian is very easy to calculate. It's going to be equal to B bold N times X, the coordinates X and the coordinates Y. Notice how B bold N is 2 by 4, this 4 by 1. So now I have really, together, I basically have a 2 by 2. I invite you to do it, you will see what I mean. So this 2 by 4, and this is a 4 by 1, 4 by 1, that's a 4 by 2. So 2 by 4 times a 4 by 2 becomes 2 by 2. A Jacobian needs to be 2 by 2. Look at the efficiency here, because we calculated B bold N once, but I can use that and plug it in here to get the Jacobian, the matrix. D bold is known. I know the conductivity matrix that's given to you. The shape functions are known. We're pretty much there. Now we have to look at this term here, how to apply heat fluxes on slanted surfaces or something like that. So let's look at how to deal with that slanted surface, that surface integral. So let's look at this one. So let's say I want to do a line integral that's evaluated. And I assume that I apply a heat flux on H23. I'm going to apply a heat flux right here. I have to evaluate that line integral somehow, this integral here. But I want to do the calculations here. I don't want to do them here. They're more painful here. So what am I going to do? Let's think about that. So H32 corresponds to this edge 3, 2. And notice how this edge is at c equals 1 at this edge. So what do I have there? I have m bold q bar hds. You can see here that q bar is really p, my heat flux. Sure, I evaluated it. It's a number given to you. And I want to evaluate this integral at c equals 1, which is this edge right here, because that's where the pressure is being applied. And that's equal to c equals 1. And what I notice here is that the length h, or this length right here, is really the square root of x, partial of x, partial eta squared, plus partial y, partial eta squared with d eta factored out. This h is the thickness of the part, so that doesn't come into play. So this makes sense. That I have to find that line integral, and now I have from minus 1 to 1. It goes from minus 1 to 1. So this ds is really the square root of all this d eta. You can see d eta cancels out, and I'll get ds. So that's clearly what that is. But this needs to be evaluated at c equals 1. So that's how you deal with this integral here. I'll show an example later on. Strategy, do everything in this coordinate system. That's where everything can be done simply. Another review of how to integrate. So say I want to integrate phi deep C numerically. All you have to do for one quadrature point, two quadrature points, is to take W and W2 from these equations, from this table. W1 and W2 is 1. And you're going to evaluate phi. You're going to evaluate phi at C1 and C2. By doing so, you calculate I very easily. So this phi, this integrand, is evaluated at these values of C. I can do that for 3, for 4, and 5 quadrature points. The quadrature for 2D elements is similar. The way you're going to go about that. You're going to have the summation, Wi, Wj, phi, Ci, eta, j. For 1 point, W1 is 4, and C1 and eta 1 is 0. So you can integrate exactly an equation that looks like this with this one single point. For 2 points, so for 4 points, 2 by 2, Wi and Wj are 1. And you're going to evaluate at these combinations of coordinates. So you have 4 different combinations. Many numerical codes use a 2-point Gauss quadrature point. So I'm going to plug in Wi, Wj, values of 1, and then plug in the 4 combinations of C and eta in here to calculate that integral numerically. So that covers the quadrilateral element formulation. I'll move now to the linear triangular element formulation that's coming up in the next lecture. Thank you for listening, and have a great day. And I hope you saw the powerfulness of isoparametric elements. Allows us to use the same shape functions for every element. The integrals are also done over a standard domain. And the derivatives of the shape functions are the same for every element. The only thing that contains the geometry of the element is the Jacobian. And that's easy to calculate, very easy to calculate.